Okay, we can go ahead and start if you have whatever questions you have.
Okay, I guess I'll start it off. So the first questions that I have are kind of just like administrative. So, like, in what lecture is that going to conclude like the test material? And then if you decided on the format of the test, like, are we going to do multiple choice or is it going to be like a normal test?
So what I've decided is that it's going to be a written exam that I will post on Canvas. You'll either download and print or download and write out. I'll give you either, well, right now, I think I'm going to post it on Friday, and then it'll be due like Monday at probably midnight. So you'll have Saturday, Sunday, and then Monday to work on it. So essentially, it's going to be like a take-home exam. And to be honest, it probably has to be at that point open book to give the honest people the same advantage as the people that are going to use their resources. So I don't honestly, I'm not concerned about. So that's going to be the exam. Exam 3 and exam 4 are going to be same format as before. But then, let me just pull up the whiteboard. But then the final exam is going to have to be multiple choice, but let's get through Easter and then it'll be multiple choice with the, we'll have to use Respondus and all of that stuff, but we'll use that ahead of time.
And then, so when does the test material end for this test?
I will, because I haven't made that announcement yet, I'm going to make that an announcement. And the material will probably go through Mondays. Well, I'm going to post it on Friday. It's probably going to be through Monday's material, I think.
Okay, so like 2 more videos probably?
Well, the one for today and probably the one for Monday.
Gotcha. Okay.
But I'm going to post an announcement after this class about the exam. Because I know, like, people moved physics and some other exams to next Friday. And I'm assuming they're doing them in class or in the class time, or they're somehow doing them online that day. So I figured I'll give you the weekend plus Monday to do this exam. And then that way I'm not overloading anybody.
Yeah, that sounds good. Okay, well, I can ask something else. So can we go over Suzuki coupling? I think it's a little bit confusing.
Okay. So, all right, so Suzuki coupling is going to be when you take the benzene ring with a bromine and you're going to couple that to some R group that's attached to what's called a borate ester. So in this case, that borate ester, how we get the R group on the borate ester is the big issue. But just if we put an R group onto the borate ester, what we're going to end up doing is using palladium and carbon and potassium carbonate, and that's going to couple the benzene ring to the R group. So the question is, how do we get the R group on the borate ester? And there's a couple of different ways to do that. So that might be the more confusing part of this, because we need to know, well, how do you make this borate ester? So in order for me to explain that, I need to go back to last semester. So last semester, we took a alkene and we reacted it with BH3 and H2O2. And ultimately what we got was anti-Markovnikov addition. So we got the H and the OH adding 100% cis, and the OH went on the least substituted carbon. Now, why am I going back to last semester? Because what we did was we added to the double bond the BH3 molecule when it looked like this. So we added the H and the boron to the double bond. So the H went on the carbon that was most substituted, and the boron went on the carbon that was least substituted, but they still went 100% cis. And then when we reacted that with the H2O2, the peroxide just replaced the boron with the OH group in exactly the same position. So if we think about this BH3 molecule in exactly the same way as the borate ester, how do I make that borate ester? Well, for instance, in this case, what I might say is well, let's take this double bond and now let's add to it the borate ester with the hydrogen on it. So now the hydrogen's going to go to the carbon that was least substituted, and the boron, the borate ester part, is going to go to, sorry, that should be a bold wedge, should go to the carbon that's least substituted, but they will go 100% cis. So one way to make this borate ester with the R group, so that entire group is my R. So the way to add an R group, one way to add the R group to the boron is to use this reaction, which is it's almost identical to what we did last semester. So it tells you, you add the H, you add the boron to the least hindered carbon or least substituted one, add the H, 100% cis. Then you would take that molecule and you would react it with the bromobenzene with then our palladium, our carbonate, and then that's going to couple the benzene ring to the R group. So in this case, the molecule is going to look like this. You're going to have your benzene ring coupled to the cyclohexane ring with, in this case, the methyl group there, and the stereochemistry would be the same. So the H and the benzene ring would both be cis in this case, because the benzene ring is going to couple and go right in the place of the boron. So we can do any reaction, we can make any alkyl group by starting with the double bond and adding the H and the BOR2. And that's before you get to the actual, that's really the Suzuki coupling step.
Is that a bold wedge that's connecting the benzene ring and the R group?
Yes.
Is there a reason for that? Did I miss you say that?
The benzene ring has to go in exactly the same place as the boron.
Okay.
So the benzene ring would be cis to that hydrogen. So they both would get bold wedges. I'll just make it a little clearer. And if you don't like that, let me write the product in exactly the same orientation as before. So here's my hydrogen, here's my, and then that's where the benzene ring would go. So the benzene ring goes exactly where the boron was. So these are just, that's the same product, just two different views of it.
Cool, thanks. Should we know the mechanism for when we took the phenol all the way to the acetyl salicylic acid?
That is a mechanism that I could ask.
Okay. That one's not bad.
Could we go over the Gilman reagents again?
Yeah. All right, so let me save this. Okay, so my context for this is that remember that if we took an alkyl halide, if we took an alkyl halide and we reacted it with magnesium, we made the Grignard reagent, which would have an R- with an MgBr+. And we could have done the same thing by taking the alkyl halide and reacting it with lithium metal to then form the R- with, well, with the lithium plus counter ion. So the only difference between forming the Grignard reagent or forming the organolithium reagent is just lithium's +1, so it's a perfect match for the counter ion, but it's magnesium 2, bromide 1, so it's an MgBr. But the idea here is that that R- it's a strong nucleophile, and it's also a strong base. And what we did with the R- last time was we added it to the carbonyl groups so that it would attack the carbonyl. So that we would form the alkoxide, and that's what the Grignard reaction was. But somebody at some point thought, you know, the R- is a strong nucleophile, so what if I reacted it with another alkyl halide? You know, could I get it to do an SN2 reaction where the R- comes in, kicks off the halogen, and I form a carbon-carbon bond? Because all of the carbon-carbon bond reactions that we learn in organic chemistry have a name to them. So somebody said, you know, carbon-carbon bond formation is really important. So maybe I could do this SN2 reaction to make a carbon-carbon bond. The problem is that doesn't work, either for the lithium or for the magnesium bromide. So what Gilman did was he decided to take his organolithium compound that he made again by taking the alkyl halide and adding lithium metal to it to make the Grignard, or the organolithium in this case. But then what he did was he added a copper 1 halide to it. And so when you add a copper 1 halide to this, the complex that you form is 2 of the anions and a lithium plus and a copper plus. So that what you end up with is you end up with +2 and then -2. So this is what's called the lithium cuprate. And it's also then called the Gilman reagent. They then found that if you took this lithium cuprate and you added it to any alkyl halide, it would actually do that. And I'm going to just put this in quotes because it's really not an SN2 reaction, but it would then couple the R of the lithium cuprate with the R of the alkyl halide so that I could do the reaction I tried to do up here, and so that I could actually then form a carbon-carbon bond. So it was the presence of the copper that allowed that to happen, and we're not going to get into the mechanism of that, but copper changes the reactivity of this complex. Because we've always treated an R- as if the counterion doesn't matter, but the counterion does make a huge difference in this case. So in our context, for the Gilman reagents, what we would say is, let's take a bromobenzene, let's treat it with lithium metal so that we can form the organolithium reagent. Let's add copper salt, copper iodide, copper chloride, copper bromide to that. So we can now make the Gilman reagent out of the benzene ring. So there's going to be 2 benzene rings, a lithium, and a copper. And so now we could react that benzene ring with any alkyl halide, and we could make then the benzene ring, we can add any alkyl group we want to the benzene ring. So the idea here is that the lithium cuprate approach, the Gilman approach, allows us to add any alkyl group we want to the benzene ring.
And so that's why, along with like the Grignard reagents, like the Gilman reagents are all considered organometallic ones.
Yeah, organometallic basically means that you have a metal in there.
Okay.
So technically the Grignards are organometallic, the lithium is organometallic, copper is definitely when you include that. And in essence, the compounds that you make, and we haven't talked about the mechanisms of Suzuki and Heck, and we're not going to, but that's all what's called organometallic chemistry because it involves a carbon-based molecule and a alkali or transition metal.
Okay, so you said the Suzuki, and did you also say the Heck coupling? Or
Yeah,
is it
the
just...
Suzuki, let me save this. The Suzuki and Heck, whenever you're taking, like in the Suzuki reaction where we took the bromobenzene and we added to it the borate ester for Suzuki, the fact that I'm using a palladium metal catalyst along with my potassium carbonate in the water, which is basically the solvent, the fact that I'm using actually boron and palladium, that makes this an organometallic reaction as well. So it just means that you have an organic compound, and most of these are transition metals, as opposed to magnesium and lithium, but they've been considered organometallic as well.
Okay, thank you.
For this reaction, do we need to make sure that like the equations or the mechanisms are balanced, or is it okay to leave it the way that you wrote it?
It's perfectly okay to leave it the way I wrote it, because I think when I've written these before, I tried to balance them the first time, and then I said I'm not going to do that again.
Okay, thank you.
Because I'm leaving products out. So for instance, I'm going to need 2 organolithiums, but then you might say, but there's supposed to be 2 lithiums. Where did the other lithium go? Well, when you make the Gilman, we're also going to then have a lithium X that takes care of where the extra lithium went, and the halogen. And then we would need basically 2 alkyl halides, and we would form 2 different products. So I'm not going to balance those equations, but that's how we would change it if we wanted to balance it.
Dr. Nichols?
Yes.
Can we go over the activated and non-activated nucleophilic aromatic substitution?
Yes. So which one do you want to start with?
It doesn't really matter. I was looking at it and just wondering, like, are we always replacing a halogen with an OH? Is that like always the goal?
Either an OH or the other reagent, which was in the online quiz for today. I think I asked you to, so this is activated, and I think I had the reagent that I gave you was NH2 minus in liquid ammonia.
Yeah.
And in this case, it's the NH2 minus replaces the chloride. So in the mechanism of this, if you replace the OH that I did in the video with an NH2, you would have exactly the same mechanism.
Okay.
But we can do that if you'd like.
Yeah, I'd appreciate it.
Okay, so just the first thing is so this is nucleophilic. Aromatic substitution. So in nucleophilic aromatic substitution, the world is exactly opposite of what it was in electrophilic aromatic substitution. Nitro groups in electrophilic aromatic substitution were deactivating groups. In nucleophilic aromatic substitution, they are activating groups. So this is an activated ring. It'll make the ring react faster, so I don't have any heat over here. But if we do this with NH2 minus, the mechanism is to bring the NH2 minus in and add to the chlorine, the carbon with the chlorine, and then actually, let me stop. The chlorine doesn't leave. Instead, this pair of electrons, in order to avoid this carbon having 5 bonds, this pair of electrons in the double bond is then given to this carbon attached to the nitrogen. So when I start this, I kind of contrast this to what we've learned so far. So when we had an allylic carbocation, we moved the pair of electrons towards the plus charge to write the resonance structure. And when you have a negative charge, you end up starting with the negative charge and moving it to form a double bond, but then this carbon has to lose a bond, so that pair of electrons goes to the carbon that's attached to it, so that it's a different way of moving the arrows when you have an anion versus when you have a cation. And this is one of the things that's way back in chapter, I believe, 2 or 3 of Top Hat. So that means when I bring the pair of electrons in to perform this bond, this pair of electrons is going to go to the nitro group. The carbon with the nitro group, sorry. So I'm going to have my Cl and my NH2. I'm going to have these double bonds in their places. And then I'm going to have the negative charge attached to the carbon, or with the carbon where the nitro group is attached. So that's intermediate number 1, or intermediate resonance structure number 1. And then what I can do is then I can take this pair of electrons, the negative charge, move it to form a double bond between the top carbon and the bottom carbon. So move this pair of electrons to form a double bond between this carbon and this carbon. But at the same time, I'm going to have to move this pair of electrons and give it to the carbon that's attached to the other nitro group. So if I do that, I'm going to end up with my second resonance structure. Right. Everybody okay to this point?
Yeah.
Okay. So I would just point out at this point that these nitro groups, to make this an activated ring, you need to have electron withdrawing groups at the ortho and para positions relative to the halogen. The reason for that is because these negative charges in these two resonance structures are going to be stabilized by the electron withdrawing group. So in other words, if I have a negative charge here, this is an electron withdrawing group that's going to be able to pull that electron density out and stabilize it. If the negative charge goes on this carbon, then it's able to stabilize, this electron withdrawing group is able to stabilize the negative charge there. So then what would happen is there's 2 more resonance structures that we can draw. So I can take this pair of electrons, this negative charge, and instead of moving it to form a double bond, let's move it to form a double bond between the C and the N. But then the N would have 5 bonds, which isn't allowed. So I'm going to take the NO bond and give it to the oxygen. So a third resonance structure is going to be to have now a double bond to the nitrogen with the 2 oxygens having a negative charge. Nitrogen is always going to have a positive charge in these resonance structures. And then down here is going to be my NO2 group, which I don't have to write out explicitly. So that's going to be resonance structure number 3. And then down here, I can do the same thing by taking this pair of electrons, moving it to form a CN double bond. But if I do that, I have to take this pair of electrons and I've got to move it to the oxygen. And I'm just going to leave the NO2 group there. And then down here, I'm going to have a double bond to the nitrogen, and that'll be the 4th resonance structure. So by being able to write these 4 resonance structures of this anion intermediate, that stabilizes the intermediate. And that's why the addition of the electron withdrawing groups causes the ring to be activated and causes it to react faster than a deactivated ring. Everybody still with me?
So you're saying that if it didn't have the electron withdrawing groups, since it's stabilized, it wouldn't react?
It would require a lot of heat, and I'll show that example in the next one, because I'm not saying that it takes 350 degrees to do this reaction. Even with the OH, even if this was an OH minus, it still wouldn't require extreme heat to get this to go. And that's what activated. Activated means that it has a faster kinetic rate than something that's deactivated. Right? Everybody still with me?
Yeah.
We need like either thumbs up or thumbs down instead of pictures or. And I can't show all of your pictures because it'll crush my Spectrum internet. Okay, so I'm going to go back to the original molecule, the original intermediate, this one. So the final step in this mechanism then is to get rid of the chlorine. So now so these four resonance structures show me why the intermediate is stable. If I ask you to do one of these problems, I'm going to ask you to write out all the resonance structures, so you have to know how to do that or be able to copy my notes pretty well. But once I have this negative charge, I'm going to take and move that here to form the double bond and reform the aromatic ring. So one of these two groups has to go. And remember that leaving groupability is based inversely on basicity. So chloride, not a base, NH2 minus, very strong base. So it has no choice but for the chlorine to leave. And so then I'm going to reform my benzene ring, which is stable. I'm still going to have my NO2 groups in their positions, but now what I've done is now I've replaced the chloride with the NH2 group. And this mechanism would be the same. If I went through and I erased all the NH2s and replaced them with OH, then it would be the same mechanism that I did in the video. So that's nucleophilic aromatic substitution with an activated ring. The activated ring having to have the electron withdrawing group at the ortho and para positions. Does that make sense to everybody, or any questions?
That makes sense.
Okay. You want me to show you what the deactivated or non-activated ring looks like?
Yes, please.
Okay. All right, so let me save these. I'm putting these captures up along with this video I will put up at the end of class. But okay, so what if I don't have? I'm gonna change the double bonds here. Okay, what if I had the chloride, but I don't have an electron withdrawing group? What if I have an electron donating group? Then this is technically what's called non-activated. And without the groups to stabilize the negative charge, if I want to do this reaction with hydroxide, it's going to take 350 degrees Celsius to get this reaction to go. And also because there's no groups here to stabilize the negative charge, so because methyl's an electron donating group, if I put the negative charge next to the methyl group, it's going to be wanting to push electron density into a carbon that already is negative. So that's not going to work out very well. So in this case, the mechanism completely changes. And the mechanism changes in that the hydroxide is going to deprotonate the ortho hydrogen. Now you might say, I didn't know hydroxide could deprotonate a carbon-hydrogen bond. At 350 degrees, it can. So the hydroxide is going to deprotonate that hydrogen. So let's think of this as an E2 reaction. This pair of electrons would go here, and the chlorine would get kicked off. So the movement of the arrows is like an E2 reaction. So what's going to happen then is I'm going to end up with a triple bond here, and the other double bonds are going to stay in place. And so I would also end up making water then, and I'd have a Cl minus. So this is the intermediate that this reaction is thought to go through, which is called benzyne. And the benzyne intermediate is really unstable. Why? Because a triple bond normally has a 180-degree bond angle. Trying to put a triple bond in a 6-membered ring where the bond angles are 120 is really unstable. But remember, we're at 350 degrees, so if we can form this, the reaction will go. But now if I have this benzyne, I'm doing this reaction with hydroxide with an excess of hydroxide. So now my hydroxide is going to come in and either add to the paracarbon relative to the methyl group, the paracarbon, and have this pair of electrons move here. Or there's nothing stopping that hydroxide from adding to the metacarbon relative to the methyl group and having the pair of electrons move there. And there's nothing stopping either way, so we're going to get 50-50. So when the hydroxide adds to the paracarbon, we're going to reform our aromatic ring with the OH group on the para position. And the negative charge will be in the meta position. If we add the ortho, or if we add the hydroxide to the meta position, then the hydroxide is going to go there. And the negative charge will be in the para position. Now you can't just react something with hydroxide. The solvent has to be water. So this C minus is going to immediately deprotonate the water so that the final product is going to have the OH group in the para position relative to the methyl group. And all I did was just put a hydrogen there. And same thing would happen over here. Deprotonate water. Put the hydrogen there with the OH here. So the idea is that when you have electron donating groups attached to the ring, it goes by this completely different mechanism. And you get a 50% mixture of para and a 50% mixture of meta.
Will that always be the case?
Yes, because there's nothing preferential about adding the OH to para or adding the OH to meta. They're going to occur at equal rates.
Mhm.
And the first time somebody did this, I'm sure they did it without the methyl group there. So they just replaced the chlorine with an OH. But then when they were trying to figure out the mechanism, the first thing they would have done is, well, let's put this group on here. And then when they put the group on there, they realized they got two different products. So whatever their mechanism is they ultimately proposed, which is the benzyne, whatever mechanism they proposed had to explain why they got 50-50, but they never would have known that you get this mechanism without putting sort of a reference group on the ring to begin with.
So there was a problem in the video where we went from benzene and we added like several steps all the way until it was a phenol.
Yes.
Is that the only example of a problem like that where we're going to have to do like, step by step how you add things? Or no, are there others?
Have you watched the video for today yet?
I watched the video you posted a couple days ago that's like
Okay.
due today.
Right, which is the one on organometallics, Suzuki, Heck.
Right.
So the one that's replacing today's class is all about taking benzene and putting different groups on the ring in different positions.
Right.
So both in Piazza and in Canvas, I posted this sheet. So in your March 20th folder, you're going to see a list of aromatic reactions, which is this sheet. Because somebody had asked me about putting together a list of all the different reactions that we did.
Yeah.
Which is what this is. So for instance, this will say, I want to add a carbonyl group to the ring. I use this set of reagents.
Okay.
I want to add a straight chained alkyl group to the ring. Well, if I want to do that, I need to put the carbonyl group on and then do Wolff-Kishner or Clemenson to make the straight chain to reduce the carbonyl down to a CH2. So as we go through and we look and see, okay, the only way we have to add an OH group is using this reaction. So if you want to put an OH group on the ring, the first thing you're going to have to do is to nitrate it, to put the nitro group on, reduce the nitro group to an NH2 group, react the NH2 group with the HCl and sodium nitrite to make the diazonium. And then from the diazonium, you can add H3O plus, and that's the only way to get the OH group onto the benzene ring.
Okay.
So in the syntheses that I went through 8 or 9 different potential ways to do that. If you see that you have to have an OH group on the ring, you have to go through these 4 steps in order to get the OH on there. So this sheet would be really handy to have while you're thinking about some of the practice problems for today. And also the quiz for Monday is not an online quiz. It's a write out sort of the transformations and then put your pictures in the Dropbox so that I can grade them. So these sheets, I don't know if this is comprehensive. I may have missed one. So in the email I sent out about an hour and a half ago, it says if I'm missing a reaction, let me know and I'll put it on. But that's what today's lecture was for taking benzene and making putting different groups on the ring in different substitution patterns.
Okay.
So Dr.
thank you.
Nichols, the sheet will be both on Canvas and Piazza for us to find.
It already is.
Okay, thank
So
you.
can you see my screen? No, you can't.
No.
No. Okay. Why was I pointing at the screen then? I'm pointing at the screen because I need to do this. I need to save this again. I need to stop sharing or go to a new share my screen. Yeah, because I'm pointing at stuff that you're not seeing. When that happens,
Thank you.
no. Okay, so you can see my screen now?
Yes.
So in your March 20th folder, there's the assignments that I just posted, and then there's a list of aromatic reactions. The list of aromatic reactions is this sheet.
Okay.
And it's also on Piazza. So it goes through the reagents if you want to add all these different groups. And so let me go back and so you can actually see it. So if you want to add an OH group to the ring, can you see my little arrow cursor?
Yeah.
So if you want to add an OH group, you need to go through these 4 steps. You need to put a nitro group on, then add NH2, then use HCl, NaNO2 to make the diazonium, and then react it with H3O+ to add the OH group. So you have to go through those 4 steps in order to add any OH group to the ring.
Okay.
If you wanted to add an OR group, like down here, if you want to add an OR group, what do you need to do? First, you need to get the OH group on there. How? Using these 4 reagents. And then you deprotonate the OH to make a phenoxide. And then you can react the phenoxide with a primary or secondary halide and put the R group to the oxygen. This is just Williamson ether synthesis. That's all that reaction is.
Dr. Nichols,
Yeah.
I don't know if it's too soon for you to know this, but are we like not doing the ACS final?
Oh, I already know that. No, you're not doing the ACS final.
Okay, so
ACS is very strict about not letting their secure exams go into any kind of internet environment. So
Okay.
they've already told us that, and we knew this anyway. I mean, I know this because I'm the person that signs off on the security pledge. So I guess they put me in jail if anybody was to photocopy it and put it online. But they don't allow an organic, they don't allow anything, well, they don't allow anything that's secure to go onto an online environment. So they already said, no, you cannot do that. For general chemistry, they created a non-secure exam that people can put on Canvas as a multiple choice final exam. But I will bet by next year there's one for organic, but there isn't now. So what does that mean? That means that that I would say the bulk of the exam that you're going to take is coming from me. If Dr. Dowd and Dr. Kwan and I decide to get together and share questions, those questions will have to be approved by everybody involved.
And is it still going to be like comprehensive from the whole year?
Absolutely.
Okay.
But it will probably be in a multiple choice environment. So sort of like what the online the online quizzes you're taking now will be. And we'll take more of those, and we'll at some point use the lockdown browser and the lockdown browser as well as the Respondus webcam thing, so that the final exam they'll probably say the final exam has to be taken during the final exam period. So if you're like not available during 8 a.m. or 1 p.m., then you need to find out when the final exam time is, and you need to block that out of your schedule, because most likely that is when the exam will be taken.
Okay, sounds good.
So yeah, that's been asked a number of times, and that's fine. I mean, I can put together a ACS like multiple choice exam. And I guess I'm going to be doing that well, you can't print. And in theory, you can't take pictures of the screen because you have to use a computer or a device with a video camera, so that if you're pointing your camera at the screen, then I'll see that. So I don't know. This might be a one-time exam because of the issue of if somebody gets a picture of it, then it goes wild.
Makes sense.
And everybody's in that position. Everybody's in the position of having to not use ACS, which is fine. We don't have to take the ACS final. We just do it to be able to assess like what topics the class was strong in, which ones they were weaker and we need to strengthen. We can do that with any kind of multiple choice exam that we create. I'm more than capable of doing that. It's going to take a while, but I could do that.
Does it count for the same percentages like a normal test would?
Yeah, and there'll probably be curve and everything else.
Okay.
We made it through 5 days of this. Only how many more left?
In that kind of an environment with the final, like I'm one of those people where I have to like write things out even if it is multiple choice. Would I be allowed to still like write in scrap paper, or is that not allowed?
Yeah, that would be fine to have scrap paper. And if everybody's taking the exam at the same time, I mean, the thing with the Respondus browser, I think or with Respondus and the lockdown browser means, and if you've used this in other classes, the lockdown browser means whatever device you're taking the exam on, you cannot open up another internet window. The Respondus means that I think a lot of people say you have to use the camera and you have to kind of like record your area so that there's nothing illegal going on. Although I don't know, maybe your phone is like up there, or maybe it just falls down, or maybe it slides across the floor, or your notes slide across the floor. But then it records you during the exam. So like if you're constantly doing that, I might get a little suspicious.
So if it's recording us and we did want to like write stuff out, would it flag that action?
I have no idea. It would flag it, but then I think if your camera was set so that it showed that, and how you do this, I'm not quite sure. Because that means your laptop would have to be like this, which isn't really conducive to doing anything productive with it.
Yeah.
I mean, we'll use our best judgment. Somebody said, if you're concerned about students cheating, they probably already are. I don't know. We're not in exactly the most positive time right now, so we'll make it work. And I have no experience with the lockdown browser or Respondus, so we'll get there. We still have 2 more exams. And a lot of days like this. Okay, just so you know, I've loaded up all the stuff for Monday. For Mondays, the lecture notes are there along with the lecture video. The chances of somebody just printing out the notes without watching the video, the chances of somebody doing that, well, they're not here to hear this. But the lecture notes are there just in case you need to consult them. The quiz, if you click on the quiz, it's going to say that there's the quiz, so you can either write it down or print it out and then answer it on paper. And then there will be because I'm the instructor, I don't see the Dropbox, but there'll be a Dropbox to upload it. In worst case scenario, if you can't upload it, email it to me. Then and if it's uploaded, then I'll just grade it online and you'll be able to see it. And that's due by midnight on Monday. So other than that, I have the morning video. I have the morning video from that meeting along with the morning meeting, along with the whiteboard notes from that are on here from 8 a.m. The video from 8 a.m. I will put the 1 p.m. right underneath it in both sections. And then there are some multi-step synthesis problems that you could do as practice. There's a lot of them there. There's probably an excessive amount of blocking in those that I might not require you to do for the exam. And I'll send an announcement about, but my plan is the exam will be available on Friday morning, and then you'll have until midnight Monday. And in the Zoom meetings, if somebody asks about an exam, I will only clarify it. I will not go through an answer like I normally do. So, and we're gonna, it'll have to be open book at that point, or I guess open resources, but it still should be done by one person alone.
Dr. Nichols,
Yeah.
how will we send you the test? Will we take pictures of it and email it to you, or?
Yeah, there'll be a Dropbox for it.
Okay.
So you'll just take pictures and upload the pictures into the Dropbox.
Okay.
Or you can email it to me as well. My only thing is I can't put anything you send me, I cannot put in the Dropbox. So maybe if you email me the pictures, I'll put them into a PDF and send them to you, and then you can upload them into the Dropbox, but I'll have them for grading. So either one, whichever one works for you.
Okay, sounds good.
I mean, we'll work through this, and hopefully it won't be too stressful. Not that at this point anything can be stressful. Why is my video not? Why is my video not showing up? Oh, because I'm sharing the screen. All right. Anything else from anybody? All right, you can put your questions on Piazza, email me. You can still make an appointment with youcanbook.me. And we can either do one-on-one or small groups if you want to organize somebody together. Or I'll answer questions on Zoom, or I'll answer questions and send something back.
Okay, thank you.
Okay, have a good weekend. One week in the can. Only how many more to go?
Bye.
Okay,
Bye, thanks.
sure.
Thank you.